Module 6, Changes in Matter and Chemical Reactions. Density. We need to begin this section with a definition of density. Density is an object's mass divided by the volume that that object occupies. And that definition can be shown in this equation. This letter is the Greek letter rho, which represents density. The m is for an object's mass, and the v is for the object's volume. So this equation is the shorthand form of the definition of density. Density is an object's mass divided by its volume. Now let's go over the units of density. In chemistry, mass is most commonly measured in grams, and volume is most commonly measured in milliliters. So the units for density would be grams per milliliter. You may remember that 1 milliliter is equivalent to centimeters cubed, so we also can express density in grams per cubic centimeters. You can actually express density with any mass unit over any volume unit, but these are the two we will use in this course. Density is important to know in chemistry. It tells us how tightly packed the atoms or molecules of a substance are. If you were to hold two balls of the exact same size and color, but one was made of plastic and the other was made of lead, do you think you would be able to tell the difference between them? The lead ball would be much heavier, wouldn't it? That is because the matter in lead is very dense or very tightly packed together, as compared with the less dense, less packed plastic ball. So density helps us figure out exactly how heavy the lead ball is as compared to the plastic ball. Lead actually has a density of 11.4 grams per milliliter. Most plastic has a density of less than a gram per milliliter. That's a big difference. There are more grams of lead packed into that same milliliter as there are grams of plastic. Now, if we had some plastic that had a density of, say, 0.54 grams per milliliter, the density of lead is 21 times greater than the density of that plastic. We know this because 11.4 divided by 0.54 equals 21. So the matter inside the lead ball is packed 21 times tighter than the matter in the plastic ball. Every material in creation has a specific density, and this helps us to identify an unknown substance. Module 6, Changes in Matter and Chemical Reactions. Experiment 6.4. In this lab, we're going to examine and explore the density of various liquids. So I have 3 liquids we're going to be working with. We have a maple syrup and oil, and then distilled water. Now, the first thing we're going to do is we have to measure the mass of each of those liquids. And to do that, I'm going to measure first the mass of my graduated cylinder by itself. If you're using a kitchen scale like this, it's probably going to have a measurement to the nearest 10 grams or 5 grams, which means you can get a precision to 1 gram of accuracy. So I'm going to go ahead. I first have this zeroed out at 0. And I'm going to put my graduated cylinder in and read it. And I have it at, my measurements go, every hash mark is 5 grams. So my measurements go by 5s. And I can see with this one, we have almost 35. So I'm going to estimate that to be 34. I'll take a closer look at that. Right now. And I've got it closest to 34. So I'm going to write down the mass of my cylinder so I don't forget that. And I have 34 grams. Okay, so now we want to measure out 50 milliliters, 50.0 milliliters of our syrup into this. I'm going to take this off of the scale. Now, when you measure into a container, don't measure like this where you're holding it. You're not going to be able to hold it very straight. So you always set your measuring container on the counter and pour into it while you're watching. And refer to the method that's explained to you in your text. We're using the bottom of the meniscus to see where that accuracy is. We want to measure out 50.0 milliliters as best as we can. So I'm going to turn it so I can see, and then I'll turn it over so you can see what I'm doing. I'm pouring my syrup in. I go a little fast till I get up close to the 50. And then you just want to kind of go really slowly. If you pour too much, you got to pour a little bit out and try it again. Get down to eye level. You can see how viscous this stuff is. Very thick. One tiny little bit more. See if I can get that drop to go in. How precise we can be with syrup, huh? Okay, so this is measured at 50 milliliters. And what I'm going to do now is I'm going to measure the mass of this measuring container and syrup together. I'm going to turn it so I can see, then I'll turn it so you guys can see. Again, my hashtags are at 5-gram increments, and it's not quite 100 grams. I'm going to say it's at 98 grams of measurement. I'll turn it so you can see what that measurement is, 98 grams. And that's the total combination of the cylinder and the syrup, 98 grams. So we know the mass of the cylinder is 34 grams. I've measured 98 grams. So the difference between those two numbers will give me the mass of my syrup. So 98 minus 34, and we get 64 total. So the mass of my syrup is 64 grams. Now I also know the volume of my syrup, don't I? I just measured that as 50.0 milliliters. The volume of my syrup. To calculate the density, I need to know the mass, and I need to know the volume, and I have both of those. So now with these two numbers, the 64 grams and the 50 milliliters, I can calculate the grams per milliliters, or the density of the syrup. I'm going to divide those numbers using my calculator, and so I have 64 grams divided by 50.0 milliliters. Let me try that one more time. 64, 50. Okay, I get 1.28 grams per milliliter. Now I have to consider the significant figures. 1.28 grams per milliliter. This goes to the hundredths place. Now I have this one is to the ones place, and that's because I'm dividing, I have to use the least precise. So my answer can only be to the ones place, and so I get 1 gram per milliliter as my answer. So let me fix that really quickly. Okay, that's the calculated density of the maple syrup. I will now wash this out completely so that I can do the next part of my experiment. But first I'm going to go ahead and pour it in here into this glass container. All right. You don't have to pour all of it out, but get a bunch of it in there. Okay, then I'm going to go wash this out, and we'll come back and do the other two liquids. Now I've washed out the cylinder, and I'm going to go ahead and fill it with water. We want to measure again 50.0 milliliters of water. A little more straightforward doing this than the syrup. You want to get your eyes at level to see that meniscus too. There we go. Turn so you can see that. So that's 50.0 milliliters of water. Now I want to take the water in the cylinder and measure the mass of both of those. Turn this so I can see. Okay, and so I'm seeing 77 grams total. So the total of those is 77 grams. But to get the mass of the water only, I need to subtract the mass of the cylinder. So I'm going to take my 77 grams and subtract the mass of the cylinder, that's 34 grams, and I get 43 grams of water. So let me write that down. Okay, to find the density of the water then, all I need to do is divide the grams by the milliliter measurement. So 43 divided by 50.0, and I get 0.86. But again, remember, we can only measure to the ones place, and so I'm going to round that up to 1. And you see, by having not super precise measurements, we get equal densities of water and syrup. Now that's not accurate because our syrup was over 1 and our water is under 1. And so because of our rounding that we have to do because of significant figures, they show up the same, but we can identify that water, remember that our actual calculated amount of water was less than 1, so less density than the syrup. So let's see what happens when I pour the water into the glass. And you'll notice that the water is in a layer above the syrup. Therefore, it's less dense than syrup. So again, remember, even though our calculated densities are both 1 gram per milliliter, our actual density of water was less and our syrup density was more. Okay, so we're going to do the same thing now with the oil. And because I used water, I don't have to wash this out. Let's see if I can open this up here. And I'm going to make sure there's no residue by grabbing this and just making sure there's no extra water in my cylinder. Drying it out. Okay. All right, so now let's measure 50 milliliters again, at this time of oil. See a lot of air bubbles coming up, so I'm going to let it sit for a couple seconds so those air bubbles come up out of solution so that I can get a more accurate measurement. Just a drop more. There we go. Yeah, I think that'll do it. Okay. So 50.0 milliliters of oil. And now we can measure the mass of the oil and the cylinder combined. Let's take a look at that real quickly. And I have, it's about 74 grams. Looks like 74 grams right there. So I'm going to write that down. Actually, no, I want to remove the measurement of the container. So 74 grams minus the mass of the container, the cylinder, 34, and we get, of course, 40. Okay, so now we can calculate the density of oil, again, to the ones place, which I have a feeling we're going to get an interesting number, 40 divided by 50.0, and we get 0.8, which is less than our calculated amount for the water, but because we have to round to the ones place, that rounds to 1 as well. However, it was the least dense calculated that we calculated with our actual numbers before we rounded them. I'm going to take this and see if indeed this is less dense than water. And sure enough, the oil floats on the water, which means it is less dense than the water. So the increasing density from least dense to most dense of the 3 liquids that we looked at would be the oil, then the water, which is more dense, and then the syrup, which is more dense than that. Again, our calculations were a little off partly because I believe our scale didn't have a precise enough measurement for us to get to those decimal places that we needed for accuracy. So try this experiment at home, and again, you kind of have an idea of what to expect, but run those calculations for yourself, and hopefully you'll get some better numbers than I got from myself.
In experiment 6.4, you should have calculated the syrup to have the largest density. It was on the bottom of the glass. The water's density was between the syrup and the oil. It was above the syrup. And the vegetable oil had the least density, and it was on the top of the glass. This is what should make sense, too, because if matter is more tightly packed together, then it will have more mass, won't it? The matter in syrup is denser than the matter in water, so when you added the water, it floated on top of the syrup. If you had poured the syrup into water instead, the syrup would have moved down through the less dense water molecules until it was at the bottom of the container anyway. The vegetable oil was the least dense of the three, so when you added it to the glass, it couldn't fall through the water and rather stayed on top of it. So in this experiment, you qualitatively determined the density of liquids by observing them. You saw the denser syrup sink to the bottom, the less dense water float on top of that, and the less dense oil float on top of the water. You quantitatively determined the density of liquids by measuring them. You figured out each of the three liquids' densities by measuring the mass of a specific volume of each of them. Qualitatively, you saw the denser liquids sink, and that was confirmed quantitatively when you calculated that. Let's take a look at a density problem together. A gold miner has just found a nugget of pure gold. He measures its dimensions and then calculates its volume to be 0.125 liters. Knowing that the density of gold is 19.3 grams per milliliter, calculate the mass of the miner's nugget. We begin with our density equation of rho equals mass over volume, but we need the mass of the nugget, so we can rearrange the equation so it solves for mass. By multiplying both sides by volume, we get mass equals density times volume. Now we can plug in our numbers for volume and density. We have 19.3 grams per milliliter times 0.125 liters. Well, our volume units aren't the same, so we need to convert our volume measurement of 0.125 liters to milliliters. So using the factor label method you learned in an earlier module, what do we have? 0.125 liters. Place that number over 1. What is the relationship between the units we have and the units we want? 1 milliliter equals 0.001 liters. Set that up as a fraction so that the liter units cancel. Multiplying through, we get 125 milliliters. Now we can plug that into our equation, and we get 2,412.5 grams. Well, we need to adjust for significant figures. There are 3 significant figures in each of the numbers we began with, so our answer needs to have 3 significant figures. We can round the answer to 2,410 grams, or in scientific notation, 2.41 times 10 to the third grams. Notice how I'm using a dot as my multiplication symbol here. Sometimes it's better to use them whenever you have lettered variables so as not to confuse the multiplication symbol with an X.